So today we're going to continue our explanation of the different types of controllers, and we're going to continue with the integral control. At this point, we had seen in another video the proportional control and the introduction to this two-part series of the different type of controllers. So let's see here. What's the background that we have right now? Proportional control produces a constant error because the control signal does not change as system reaches equilibrium. Okay, so the more error, the more control result, there is an error in the end, steady state error. What we would like as an objective is to modify the control signal as long as the error exists. So now you're going to say, look, if you have an error, I am going to use integral control to get rid of it. Okay? So how do you actually implement this? A signal that represents integral control will have a constant, which would be the integral control constant, and then the error here, we're going to multiply by an integrator, in this case by 1 over s. Remember, s means differentiation, 1 over s means integration. Okay, so that's what this is. And the equivalent of this in the time domain would be to integrate from 0 to t e to the edt, and with the conditions 0 initial condition. K sub I is your integral gain, and Fs would be the deviation in the control signal. Okay. Here's an interesting note. It says the control must be reinitialized. Otherwise, integration could continue. When you really want to be reinitializing to be acting depending on the error, right? If the error is not there and you fix it, then you're done. So here we go. This is an integral control example, a velocity servo with integral control. So you have in here the transfer function of your system, and this is the measure of the angular velocity. Then this is the reference of the angular velocity. The difference between these two signals will produce an error, which now, not to confuse things, we are not going to use proportional control and combine it with this. We will do that in a little bit, but right now it's pure integral control. In here we have the disturbance here. So if the disturbance is 0, then we could just do this simple loop. And this is how it works. If you identify each one of these blocks to the physical system, the summation, here's the DC motor, which is this, plus the load. This is your system right here. All right. Let's see if we can actually do this. Yes. See right here. This is your system. So why don't we say system? And you measure here the angular velocity here. Well, no, here we have capital omega. This one. Yeah. That's a tachometer means you're measuring speed here. You're feeding it back here. This is what you what you see, this is your difference block right here. Power amplifier actually is your control here. See? So here's where you have the control. But mathematically here, you're going to see a transfer function between the input and the output. You know, this ratio, when this ratio is 1, then you're really cool. You know, the system works fine. But in the meantime, when the angular velocity compared to the input is 1, then you have reached your your goal. You can have a transfer function. How many inputs do we have? We have, let's see, we have, let's see, pen. We need, I'm trying to change the color. Let's try this so that we can actually read this a little bit. How many inputs do we have? This one, this is input 1. All right. And this other one, that is the disturbance, this too is an input 2. Yeah? So, remember what the transfer function is? Is always some output of S in relation to some input of S. So if the output is this, is going to have a transfer function that would be omega with respect to the input, which omega t in here of S. This is transfer function 1. But you see, this is also an input, and you can have the transfer function of omega with respect to the disturbance, yeah, and this will be transfer function 2. This transfer function 2 is this. Transfer function 1 is that one. Okay, so let's make no mistake that a transfer function always is between one output and one input, okay? That way you can understand exactly what's going on in here. We can modify the system by changing some physical parameters, or we can change the controller by implementing these gains for proportional or integral control. But the concept of a transfer function remains a relation between one output and one input. Okay, let's just look for another example in here. This is an integral control system. As you can see here, the plant, which becomes there is this is your system. Motor and disturbance, torque, all that. This is your system. Okay? And this is the measurement right here. This is where you actually measure. Yeah? And this is, so you measure the feedback in here. You make your comparison. You know, right here you make this comparison, and then you have the amplifier, which would be, this is your control right here. in this case, integral control. Yeah? And then, of course, the disturbance in here. So the difference between what we have done with the previous and this example is that the transfer function is a higher order, because this is second order system. And you have the measure of the with respect to the original. This is a position control system. I mean, if you have a transfer function that measures the velocity, isn't it true that if you multiply by 1 over s, in other words, if you integrate, you get the position, right? That's what's going on here. That's why the denominator is cubic as opposed to the other one, which was a square here. And you have the other transfer function would be the disturbance right here. This disturbance is this. And the corresponding transfer function between this output and this disturbance input is this one. Okay, so the more we do this, the better. Problem is that if you integrate this, you could, by multiply by 1 over s, what are you doing? Okay, let me see if I can help you reach a conclusion. That 1 over s has to be multiplied with the existing polynomial of the denominator of the transfer function. If you multiply s by, let's say, s squared plus 2s plus 1, and you multiply by s, that factor isn't it true that it has a pole at 0, right? Let me just draw it here so that, see what I'm trying to tell you is, if you have, let's say, something like a divided by s plus s squared plus 2s plus 1, let's say. We're going to put a or k, it doesn't matter. And now you come in and you say, you're going to multiply by 1 over s. What have you done? Isn't it true that this term induces a pole right here? 0. And isn't it true that this is the oscillations section? And this guy is the unstable section, right? So you gotta be careful to do this integral control, because if you do it too much, you could bring the system on the right hand side, and you could, because you were trying to eliminate the error, now you created a major problem because it could be unstable. So be careful. System is unstable with integral control. The final value theorem cannot be applied, and the integral control improves steady state error, but it could produce an unstable system. So integral control is like, you may say, like the medicine, but don't do it too much, because you could actually mess it up. That's the point here. Integral control will degrade the transient response because now the system oscillates. So if you want some response fast and that it would be stable, this is not the thing to do. If it is something that we need to control very precisely the position of something and that the error is not there, then this is the thing to do. Okay? Then we have the next kind, which is derivative control. Remember that S is d dt, yeah? So if we multiply by s, just needless to say, 1 over s was the integral, right? This is what we just did. Now we're going to go the other way. In this case, we have this problem. We say integral control produce control signal error after and produces an unstable system. The idea would be to make a controller react to the derivation of the error with the derivative control law. You know what it does? Put this in your mind. This thing dumps oscillations. See? So if you want to attenuate any vibration of the system, you introduce a bit of derivative control. Now, these are like the ingredients, You may say that, like, when you're cooking something good that you like, you have several ingredients, and then you put this, a little bit of this, a little bit of that, until it's to your taste, right? That's exactly how control systems work. Depending on what you want to do, you may want to introduce some derivative control to damp the oscillations, or you might introduce a bit of integral control to control the error, and you might have proportional control to do it quickly, which means that either you could have a proportional integral control, proportional derivative control, you could have a PID controller, proportional integral and derivative. So you see, it's not like it's arbitrary or that in every situation you have to have all these three. That's not the case. But what is the case is that um, you could have a combination of this. See, like for example, this is PD control. This is PID control. So you have um, proportional constant. You have the derivative controlling here, yeah. Or you could have this one, proportional, integral, and derivative control. All of this proportional to the error signal. Okay, I think we have established the principle about which this is founded, let me say. So here in a servo mechanism, for example, you have the system right here. You measure here your feedback, but this is your controller, see? Now, the controller has a combination of this. And then this, what do we get with this? Say we don't get a deviation resulting from the disturbance, which is good, but improvements in the transient response over the proportional action are desired. Integration action may not be required, and the rate of action can improve the transient response. See here what we have done? This would be the transfer function between this and this. That's what this is. And if you have it, if you want it between this and the disturbance, you have this transfer function. But you see, this is how you implement the different kinds. It's a stable system, much more stable. Does not affect the steady state response, and the steady state response are identical to those of proportional control, meaning there will be an error. Okay, so you could damp a vibration but still produce an error. Okay, deviation of 1 over kp would be due to the disturbance. If you come to a PI control, you have this kind of background. Proportional control produces steady state error. Integral control corrected the steady state error, but degraded the transient response, meaning becomes the system unstable, or have the tendency, you would say, to the system unstable, depending on how much of this integration you have. But we want to combine the instant, so I would say combine the instantaneous response characteristics of proportional control with the zero error steady state characteristics of integral control. And this is what you'll have. See, you have proportional control here, and then you'll have the integral control here. This is just to express it in a little different way. Um, right? Just a bit of algebra, but the concept is this. Okay. Um, so this is the PI controller. This is a concept that we should take a look at. The damping ratio is in fact a measure of how much damping there is on the system, right? This what are the advantages? Kp can be large to reduce steady state deviation due to the disturbance. So your first line of action to correct something is the proportional control. The Kd, the derivative control, we can achieve a specific damping ratio. And then Kd helps us to stabilize the system by adding damping, but the system is not stable, or when the system is not stable. Here is the one type of controller that if you build this your control block like this, you may approximate the differential control. Okay, so but let's concentrate on the main thing. This is the what we're doing here on this slide is if you build it like this, in fact you are building a derivative control. Okay, so in this case system is more sluggish than with pure PD control. Similar characteristic equations, and this the case could be chosen to be given the specific ratio. Alright, so if you make this little change in here, the steady state performance, for example, would be very good. Okay, let's just reach some conclusions of PI controls. Steady state for positive values of Kp, the offset error is 0. You can modify the damping ratio and select the damping ratio by fixing the dominant time constant. You can do a few things by changing the physical parameters to modify that. Okay, so there are the two constants, one to determine the damping ratio, and the other one used to also to set the damping ratio. But anyway, these are specific examples that I would like you to consider. Um, one was for first order system, this was for second order system. This, for example, we will look in another, let's start another series and on a third part, let's say, on pneumatic liquid level controls and other examples of these type of controllers. So we're going to stop now.